I guess that is what we will get. Okay, good afternoon, everybody. Once again, the technology is refusing to cooperate, so I have no sound for you today, and there's nobody in the room. Oh, well, at least I can sound a little bit clearer there. So you will have to rely on the chat in order to ask questions and commit answers. So today we're continuing our rush through the geometry foundations, hitting those very basic vocabulary terms. Today we're going to talk about quadrilaterals, the defining features of the, I was about to say like 4 basic food groups, but I guess there's technically more than 4. The 6 basic quadrilaterals, and circles and their general pieces and properties. But before we do that, let us go back to yesterday's work on polynomials and triangles and check how we did. Here I have my answers there. We got through most of this together. The dodecagon turned out to have 54 diagonals. That's quite a lot. And if you worked out the formula, that would be right here, n being the number of sides of the polygon, so n times n minus 3, all divided by 2. It's a handy little shortcut to know. It's not critical, it's not important, you will not need that. Any question relating to diagonals you could probably work out on your own, but it's a nice shortcut, possibly useful on the SAT. Right, then here is my completed concave pentagon. They do give these letters in order, and when they are given in order, you want to be able to work your way around the shape, labeling those points in order. So the fact that they give you the diagonal, external diagonal must be ET, that means N has to be in the middle because it's between E and T. So they need to be in this order and marked up as such. And please use a dashed line for this external diagonal so that we don't get it confused with what should be the shape. And otherwise, wait, is this a trapezoid with a triangle in the middle? Or no, it's supposed to be the pentagon, and this is the diagonal. So dashed lines for diagonal, for a general distinction there. And then here's my equilateral quadrilateral. It's a lot of laterals. But we will see later today that's known as a rhombus. And please make sure you have marked the angles Q and U as different. Okay, so a different number of tick marks to show they are definitely not congruent. Even though it should be pretty obvious from looking at them. One's acute and one's obtuse. But, you know, you could have tried drawing a square, but no, a square wouldn't have worked. It's got to be a rhombus. Square would have congruent angles. Anyways, moving on. Here is 15 through 18. Again, all these numbers can be read off of one shape or the other. They do write the names in a particular order so you know what corresponds to what. MNOPQ corresponds to RSTUV in that order. So N is the second letter, S is the second letter. Those vertices are the ones corresponding to each other, so those angles will correspond. That's how you know N has to be the 82-degree corner. And if you want to put this shape on top of the other, I think you would actually have to flip it over. You can't just rotate it like I demonstrated yesterday. It'd have to be a pancake flip over. Package delivered, yay! Got a new shirt, I'm so excited. Anyways, the perimeter then of a regular pentagon. Regular means all sides are the same, so I can just divide the whole perimeter by 5 to find the length of each one. Are there any questions on that first page? No? Then let's go on. Second page. Name a pair of all of these things. There are a number of ways you could have answered each of these. I'll talk a little bit about them. So here's one example. Parallel, there's only the one set of parallel lines. It has to be from these two lines. This one can only be named AB or BA, right? Those are the only letters you can use. This guy, though, you could have used any of these two letters, G and H and I, or G and I. Any of those would do. Perpendicular, there is only one intersection we know is perpendicular. That's this guy right here. It's the only one marked with the 90-degree corner. So it has to be some combination of this line segment and something from this line. And they don't actually need to intersect. You could go all the way over and do like CD is perpendicular to BF. That would technically be true. The congruent segments, similarly, there's only the one set of segments marked. It's got to be CG and HF or FH. Again, you can swap the order of that letter there. That's okay. I'm going to get back to the supplementary angles in a moment. Let me skip ahead to the linear angles, because this one's a little easier. Linear angles form a line. That's part of the name. So any two angles, so DEG and GEF, they combine to form this line here. There's lots of examples of this. You know, ADE, EDG, right? Any of those combinations there, HIF, FI, there's not a letter there. So that angle, yes, would work, but you don't have a way to reference it. So any of those could be a linear pair of angles. Turns out a linear pair is also supplementary. It takes 180 degrees to make a full line. So any answer you have on 5 could also be an answer for 4. That would work just fine. I've gone for something a little bit different here just to show off another possibility. You could use, for example, angle BAD and DGH. Those will be supplementary based on the property of the parallel lines, which we will talk about more next week. So that's a bit of a preview for you there. Those ones will also end up supplementary. They are not necessarily right angles. Please do not confuse that. They look pretty close, but maybe they're off by half a degree. You don't know. It's not marked. All right. Moving on, the rest of my isosceles obtuse triangle, try, it's right there. We did most of that one together. And then the scalene right triangle, so indicate it's right. Any of the angles could have been right angle, but the midpoints need to be on the correct segment. So it tells you L is first on segment SC, respectively. That's what that means. That means the order in here matches each one. So L has to be the middle of S to C. M has to be on C to A. And I know they are midpoints. It's not just any old point. But the only way to know it's a midpoint is to mark both sides of the segment as congruent. This half is congruent to that half. And I know it's scalene because I have marked them all with a different set of tick marks. So this side has the 1 ticks, this side has the 2, right? So I know that these should not be congruent. Otherwise, I would have made all 4 of them the same ticks. Okay? And then finally, we have 10, 11, 12, the coordinate. There's lots of possibilities here. I've written down one, but I'll talk about what else you could have. Point F could be anywhere along this vertical line. Would give you another right triangle because it's anywhere on this line. It would automatically have the right angle there. Similarly, it could be anywhere along the y-axis itself. Would also automatically make a right angle here at A. So as long as your x value is either 0 or 8, any F coordinates will do. Similarly, D, it's got to be ABD. This line has to be part of your triangle. So the only way to make it isosceles is to make these two halves the same, which comes by putting D right in the middle. So anywhere along this line, your point D will make an isosceles triangle. So as long as your x value is 4 for D, it will be correct. And then finally, G is even more freedom. You're trying to make a scalene triangle that's not a right triangle, so it just cannot be either of the other two. So as long as your G is not 0, not 4, and not 8, it will work. It could go literally anywhere else. Although, technically there's probably some combination out there that will accidentally make AB the same length as GB, I'm sure, but you're not going to get that just as long as you're on the intersections there. All right, any questions on that page? No? Then let's move on to today's topic. Starting with quadrilaterals. What are the defining traits of the basic quadrilaterals? All right, that's what we're going to focus on, just the defining properties. In a couple weeks, we will talk about quadrilaterals specifically, and we'll look into more properties as a result of. But for now, we're going, what is the bare minimum required to make, say, a parallelogram? I can have any 4 sides makes a quadrilateral. But what makes it a parallelogram is that I have 2 pairs of parallel sides. So these sides are parallel, and these sides are parallel. It can be any length. And just to make sure we definitely know they're supposed to be parallel, even if I didn't draw them perfectly, we mark them up as such. I'll let you fill in the letters there. So that gives us our parallelogram. That is the minimum, that is the definition of parallelogram. 2 pairs of parallel sides, right? Or all opposite sides are parallel. Okay? And we can get more specific if you make a parallelogram that has all 4 sides congruent. You will end up with a rhombus. And that's not quite right. This one needs to be a little bit longer. That looks better. I know I'm getting a little picky here. All right. So make sure you mark them. They are still parallel. So we still have the arrows. And we have a single straight tick mark on each of them, or you can go double, triple. It doesn't matter how many ticks you use, so long as you have the same number of straight ticks on all 4 sides. So that's what makes it a rhombus. All 4 sides are congruent. And then we can get even more specific. If we take a rhombus and set all 4 corners to be right angles, we will get a square. So we need to include all those same properties. So opposite sides are parallel. All 4 sides are congruent. And all 4 corners are right angles. Lots of marking up on a perfect square. Okay, I'm going to skip around a bit. Down here on number 6, they ask for rectangle. Rectangle, roll it back, is a special kind of parallelogram, but instead of the congruent sides, what we get is congruent angles. We make all 4 angles into right angles. We end up with a rectangle. Opposite sides are still parallel. Please mark them as such. So a square is a rectangular rhombus or a rhombic rectangle. A square is both rhombus and rectangle at the same time. And all of them are special types of parallelograms. That forms the core family of 4 quadrilaterals there. And then we have the 2 odd guys out. We've got the trapezoid here. A trapezoid is defined as only one pair of parallel sides. And there's several ways you could draw a trapezoid. We could draw one like this. Those are supposed to be straight sides. And set these parallel. But we want something perpendicular in here. So I'm going to adjust my trapezoid to accommodate. And I'm going to make it like this, almost, but not quite rectangular. That way we get one pair of parallel sides as well as at least one right angle. And now we will be able to label some additional points to get parallel. Please notice, I highlighted number 4. This, filling out the rest of this question is going to be a little tricky because it's trapezoid TRAP. So the 4 corners of your trapezoid need to use those letters. But they're also referring to segment RE. So you need to put an additional point E somewhere on your trapezoid to meet that property. Okay, I'll leave you to figure out how that would go. But that is our, this is a right, because it's got the one right angle, trapezoid. And then the other interesting quadrilateral we can make is a kite. And a kite is defined as having 2 sets of adjacent congruent sides. What do I mean by that? Well, if you look up here at the parallelogram, turns out as a result of opposite sides being parallel, when you do that to all 4 sides, you're going to get the opposite sides also end up being, oh, I didn't land right on top of it. I want to go across the line. There we go. Opposite sides also end up being congruent. That's not one of the defining features, but it is a direct consequence of the 4 parallel sides. You get opposite sides are congruent. So they took that and said, what's a different way we could arrange those? And said, what if instead of opposite sides, we made adjacent sides, 2 of them that are next to each other, congruent? And that's how we end up with a kite. So it's not the opposite sides, it's the 2 sides next to each other. You get 2 pairs of adjacent congruent sides makes the kite. All right, there you have the whole quadrilateral family. Any questions there? No? All right. The other questions here have you identifying and naming the shapes out of this figure there in the grid. So you're going to have to use the features of the grid to know, okay, this is 1 length, and so that is 2 length, and so you got to match up, figure out which sides are going to actually be congruent to each other so you know which piece is which. But for now, we're going to move on to circles. All right, lots of information to cover with circles. Let's start with the very basics. This guy right here, that round bit around the outside, is the circle itself. And we refer to a circle by its center point. So this will be called circle O, because the center point is labeled O right here. All right. The shorthand for circle is a circle with a dot in the middle, so that is also circle O. Right, similar like we've seen triangle A, B, C, you have circle O. Okay. And that circle has a diameter. Let me use a slightly thicker line here. QP is the diameter of the circle. It is a segment that stretches all the way across from one side of the circle to the other. Similarly, we could talk about the radius, right? Another very important part of the circle. And the radius is a segment that goes from the center to the edge of the circle, anywhere on the circle. And the defining feature of a circle is that the radius drawn anywhere is exactly the same length. A circle is in fact defined as all of the points the same distance from a single center point. Okay? So no matter where I draw this radius, it should always be the same length. And there's a lot of seemingly tricky geometry puzzles out there that take advantage of this fact. A lot of people tend to forget, oh wait, this is in the same circle. Oh, these two lines actually have to be congruent. So it's easy to overlook sometimes. Deceptively simple idea. All right, that's the easy stuff. That's third grade level, right? We've heard those terms all before. Here is the new stuff. What we have down here, this guy, this 48 degrees, is called a central angle. Angle QOR is a central angle because its vertex is on the center of the circle. All right, I could draw central angles anywhere I like, as long as the vertex is in the center. If you draw some angle, let's say I like connect here. This is not a central angle. It's just a rather ordinary angle in the middle of my circle. It doesn't really have a lot of special features. We do, however, have another special type of angle you could draw in a circle. I'll make an example of one right here. This is an inscribed angle. Okay? And it's inscribed because its vertex is on the circle. We'll talk more about inscribed shapes a bit when we get to question 5 down there. But the pink guy is an inscribed angle. The orange one is a central angle because its vertex is on the center. Very easy to identify. Now, the special thing about a central angle is it also defines something else for us. It cuts up the pizza into individual slices, and the crust of which is called an arc. So we can talk about arc QR. And we identify an arc with a curve piece above the letters, not to be confused with a segment. There's a definite curve there. In fact, let me draw in segment QR so you can see they are definitely not the same thing. All right? Arc QR is not congruent to segment QR. One's a curve. The arc is a part of a circle. It has curvature to it. It's a little bent. Segment QR is perfectly straight. All right, it connects them immediately. arc goes along the curve of the circle. And we define how much of the circle that arc is by its arc measurement. And the measure of this arc is equal to the measure of its central angle. So in this case, that would be 48 degrees. An arc is measured by its central angle. The measurement of arc, so it's 48 degrees of arc. This is a 48-degree central angle. Those two are always, always, always equal to each other. Those measurements are equal. And then we need but a few more pieces of information. One really, but from that we'll deduce another to be able to answer the rest of these questions about other arcs on the circle. What are their measurements? What we need to know is what is the measure of the whole circle. How many degrees around an entire circle? Type it into chat. Skateboarders would be really familiar with this. If you do a trick and you spin all the way around, how many degrees is that? I've got two answers so far. Fine, I need some more. How many degrees in a full circle? Sure, you've heard it before. Run a quick Google search. Ask Siri if you have to. There's one more answer. They are all correct. That would be 360 degrees for a full circle. Spin you all the way around. Do 360 degrees. Which means, all right, so the rest of you that did not answer, you answer the next question. How many degrees in half a circle? Ooh, very good, Jackie. Yeah, half a circle is, and I don't have a symbol for half a circle, so I'm just going to draw it on here in another color I haven't used yet. I guess that'd be brown. So half a circle up here would be 180 degrees, half of 360. So if you've ever heard somebody, he did a complete 180, right? He changed his mind entirely from yesterday. Yesterday you were saying the opposite. Now you say this, you've done a complete 180. He's turned around to the opposite, half a circle. So knowing that the whole thing is 360, half of it is 180, this much is 48 degrees, you should be able to easily add and subtract to find the measure of any of these arcs as indicated. Okay, a few more concepts to go. We've got inscribed and circumscribed. It's right there in the name. Scribe means to write. Inscribed is written within. So within my circle, boom, look at that. Oh, I love this program. My perfect circle, I can inscribe a pentagon. Does that mean I draw a pentagon inside my circle just anywhere? Not exactly. To be inscribed, it must be not only inside the circle, but with vertices on the circle. And I don't just mean some of it. Can I get that back again? Nope, you have to do it this way. All right. Don't just mean some of them. Here I've got two vertices touching the circle. I need a bigger pentagon because all the vertices must touch the circle. All 5 points there on my circle. That is an inscribed pentagon. And then similarly, but opposite, we've got a circumscribed shape. And circum means around. So writing around something. If you circumnavigated the globe, you've traveled all the way around it. So here I have the opposite case. Here is my circle. And if I want to circumscribe a quadrilateral, I have to draw it outside of the circle, right? And can it just be anywhere outside the circle? No. It must still be touching the circle, like that, and go like that. There we go. It doesn't have to be a perfect square. But you must have all 4 sides touching the circle. Okay? Right there, that single point, it just touches the circle. And we call that the point of tangency, or a tangent line, a tangent point. That's what tangent means, to touch. You'll see that term come up a lot. This is where it comes from. All right? A single line touching a circle at a single point. All right? Now again, you don't have to draw these as perfectly as me. Just sketch out your circle, and it says a quadrilateral. It doesn't even need to be a square, so you can make them as long as you want. There, there, and all right, draw your next one. Whatever. Oh, nope, that goes too far through 2 of them. Go like that, and yeah, right? Quick sketch. That's all we're looking for there. So that's those 2 new terms, inscribed and circumscribed. And then finally we get to number 7. Number 7 is a circle on the coordinate plane. So as I said before, SAT is going to love throwing geometry combined with algebra by sticking things on top of the grid and asking for specific coordinates and being all precise and graphing all this. And it's actually not too bad. So think about, before we get to this one in particular, think about a more basic setup. If I have the unit circle, so centered at the origin, 0, 0 right there, and my radius is 1, okay? So it's going to go through the x-axis right here at 1, 0. And then straight up from there, this far, also radius of 1, so that distance is 1, but now it's in the y direction, so it's 0, 1. And then on the left-hand side, we have -1, 0. And down here, 0, -1. That's my unit circle. And so the, excuse me, the easy 4 points to define on any circle on the Cartesian plane is in those 4 cardinal directions. Think of it as a compass rose, north, south, east, west. Those will always land nicely on grid points. If my radius is an integer value and my center is on an integer intersection, then I will have these 4 points will be nice handy integers, and I don't have to worry about trying to find, some point out here that's, 0.375 comma, whatever, right? We don't have to mess with any of those fractions. And then we can expand our circle. It doesn't have to be a radius of 1. Any integer value will do, so you could even go one bigger, and we could connect up the 2's and make a radius 2 circle, right? So that's what we're looking at over here. Whoops. You need to figure out what is the radius of this circle, how far is that distance from the given center out to one of its edges, and notice the curve they give us here suggests the rest of our circle is something like that. So where are these other 3 out of those 4 cardinal points? Okay, determine the coordinates thereof. You're just going to add and subtract the radius from the center's coordinates. Okay? Not terribly tough, but it does require you to think about it a little bit differently. Okay, any questions on the circles section? No? All right, then you have, looks like about 9 more minutes left to work on the rest of these questions and get that turned in by the end of the day.